Dear colleagues, sorry for being a poor replacement for Gustav Henter, but for some reason he didn't show up. So I will chair the session and introduce Thomas Drugman, which is actually, I think, is not necessary because most of you know him. So he's currently science manager at Amazon TTS research team. He received his PhD in 2011, University of Mons, and winning the IBM Belgium Award for best thesis in computer science. So since then, in 2014, he joined Amazon as a scientist in Alexa team, and he then transferred to the TTS team in 2016, where he is science manager since 2017. So he has contributed in making Amazon's neural TTS more natural and expressive. So we are looking forward to an interesting talk about expressive text-to-speech. So Thomas, the floor is yours.
Thanks a lot. And I see you compete with the beard of Gustav, which is good. I could not do that. All right, let me share my slides. I assume you can see that. And very happy to have you on a Saturday morning. And I'm going to talk here about expressive neural text-to-speech, or at least my goal is to give you an overview of the research activities we are doing on this topic in Amazon Alexa. And I'm Thomas, as you said, I joined the company 7 years ago and transitioned to an applied science manager role 4 years ago. My first slide is, what is an applied science manager in a big corporate like Amazon? I added that slide because, to be honest, still a few years ago, I had no idea. So let's break it down. We have applied science here, which is actually pretty cool. In our case, it means we go from end to end. We start from the need of a customer or request from a product manager, and we start from that blank page, and we go up to the very end, which is the feature release or the launch. And basically, we have a blank page there, and it's up to us to define the how. And along our way, we have to answer multiple research questions. So that's for the applied science. Manager is a bit less sexy, but we do need managers, right? But there are 4 pillars for a technical manager at Amazon. One is people management, so it's everything around managing the performance, growing people, working around their career development. Then there is traditional project management, so tracking, reporting, working on risk management, stakeholder management. Technical supervision, because the team is technical, so we have scientists and software developer engineers, so we need to make sure they're on track and to remove obstacles from the path to delivery. And finally, the last pillar is less tactical, but more strategic, and it's everything around business/product development. So working on a 2-3 year strategy. All right, and of course, the ratio between those 4 pillars really depend upon your level and the cycle in the year. So that's an applied science manager, and I am part of the text-to-speech team at Amazon. We have 2 main products. One is, of course, Alexa, which we released in November 2014, which now you can find in a wide range of devices, and that's available now in 16 languages. So Amazon Alexa, the other one is Amazon Polly. It's a text-to-speech service as part of AWS, so Amazon Web Services, which is now available in 63 voices and 29 languages. And I'm working in the text-to-speech research team, and our goal is to improve the core technology, which is voice and language agnostic. So once the technology is improved, we then hand it over to a more production team, which is responsible to apply it to the portfolio of voices and languages. So I'm starting here with the context, but of course I will get narrow. So we are working on Alexa. Personally, I find it, but same for similar products from competitors, but I find it technology-wise very remarkable, especially if you think it was launched 7 years ago. And there are different modules in Alexa. There is the Alexa voice service, wake word detection, automatic speech recognition, natural language understanding, and text-to-speech. So as you can guess, there are quite a big number of people working on it. And if you think about the whole interaction with Alexa, so if you say, Alexa, what's the weather in Budapest tomorrow? The very first thing is the wake word detection, which is done on device. So in our case, wake word is Alexa, and then it triggers the whole interaction. Then the audio is streamed on the cloud, where you can find the Alexa voice service, which behaves a bit like an orchestrator interacting with the different modules with the different components. The very first module is automatic speech recognition. So we send the audio, and DSR returns a recognition result under the form of an best list of hypotheses. So far it's just text. I mean, it's just a sequence of letters. We need to understand it. We need to interpret it. So for that, we have the module of natural language understanding, NLU, which basically performs two operations. One is intent classification, and the other one is name entity recognition. So basically that means if you ask what's the weather in Budapest tomorrow, we understand it's a weather intent, and that Budapest is a location and tomorrow is information about the time, right? So that information is then returned to the Alexa voice service, which is then going to route, depending on the intent, which is going to route to the right Alexa skills. So the Alexa skills can be developed by 1P, so first party, but also 3P, third party developers. So in our case here, it would be the weather skill. So this intent is sent to the skill, which then turn it into a play directive, which is sent back to the device together with the response from Alexa. So that's where we, as TTS team, take place. So I'm not going to focus purely on TTS. As you all know, in TTS, in the TTS development cycle, there are multiple steps in this pipeline. As scientists and engineers, we all love TTS system building, which will be the focus here of my presentation. But I don't want to lose sight of the fact that we have data collection here, where usually we need to rely on 20+ hours of recording. So that means we need to bring we need to contract to source and to contract a voice talent to bring in studio and so forth, right? So it's a time-consuming and costly process. Evaluation, we are working on generative modeling, and in TTS, unfortunately, we don't have any good proxy of an objective metric, right? We still need to rely on those subjective evaluation, which again are time-consuming and costly. So just saying, I'm going to focus on TTS system building, but let's not lose sight of the fact that those two processes, data collection and evaluation, they can be processes that we need to improve also in the pipeline. And I'm going to focus purely on neural text-to-speech here. We use three, all of you know that, right, I guess. So we start from the text, perform some text analysis, namely text normalization mostly, and G2P, grapheme to phoneme. Then we have some linguistic features, so here phonemic features that go into an acoustic model, and then audio synthesis using a neural vocoder. And so neural text-to-speech means that acoustic modeling and audio synthesis are purely based on deep learning. For text analysis, so the front end, I'm not going to focus on the front end, but you can find also some rule-based approaches. So let's focus on acoustic modeling and audio synthesis. We start from phonemic, possibly linguistic features, but let's assume here we have a sequence of phonemes and some information about punctuation. So that fits the acoustic model, which is a sequence-to-sequence network. That's focused on the speech representation. And the acoustic model is dependent upon the speaker and the style, right? And its goal is to reconstruct another sequence, which is the MEL spectrogram. This MEL spectrogram goes into the step of audio synthesis, where the goal is to reconstruct here the audio samples. So it's a neural vocoder, which we hope to be universal. So I'll come about that point later on. So here it's purely focused on the high fidelity reconstruction of the signal. And we hope, because it's universal, we hope it to be independent of the speaker and the style. Our acoustic model, so we start from sequence of words. We use the grapheme to phoneme, G2P, to convert into a sequence of phonemes that go into a main encoder. So we have this phonemic embedding here, feeding the attention model that is controlled with the attention weights. and then goes into an autoregressive decoder to reconstruct the MELT spectrogram. Our model is essentially builds upon Tacotron 2 from Google 2018, I think, which is now pretty standard. And that's an acoustic model containing a few dozens of million parameters. The neural vocoder is based upon parallel WaveNet. So WaveNet by Google 2016. So where we have this teacher-student paradigm, and we feed the MELT spectrogram. So not linguistic, but MELT spectrogram information here. And again, it's purely deep learning and contains a few millions parameters. So when you put all these pieces together, we obtain a neural text-to-speech technology, right? Which really is at least for US market at the end of 2018 for Alexa. I'm going to play a sample here. So we have our hybrid unit selection technology here, right? And the first neural text-to-speech samples we got at the end of 2018. So I'm going to play the samples for this text here.
Introducing Amazon's first custom electric delivery vehicle. Amazon has revealed its first custom electric delivery vehicle, designed and built in partnership with Rivian, and expects to have 10,000 of the new vans on the road delivering to customers as early as 2022. Introducing Amazon's first custom electric delivery vehicle. Amazon has revealed its first custom electric delivery vehicle, designed and built in partnership with Rivian, and expects to have 10,000 of the new vans on the road delivering to customers as early as 2022.
Okay, so as you can hear, I guess we have intelligible and natural speech, and if we compare, this new neural text-to-speech compared to the previous technologies for TTS in this 2D plane here. So on the x-axis we have naturalness, and on the y-axis we have flexibility. Flexibility in terms of ability to create new voices, new styles, more expressive and potentially controllable technology. So if you remember, still 5 years ago or so, we were, the research committee, we were still working on statistical parametric speech synthesis. I'm going to play a sample here. It's a bit outdated, probably something like 10 years when I was in academia, but still gives a sense of the quality we got.
Alice was beginning to get very tired of sitting by her sister on the bank and of having nothing to do.
So naturalness is low, mostly because of oversmoothing and the fact that we use these parametric vocoders. So naturalness is low, but SPSS gave the hope of going towards more flexibility because we rely on statistical modeling. Now I'm going to play the samples we have for hybrid unit selection and so deep learning generative models, so neural text-to-speech as I presented here.
Hello Budapest, hello SSW. This is a sample generated with hybrid unit selection. And, as a point of comparison, here comes another sample generated with neural text-to-speech.
So as you can hear, both are fairly high in terms of naturalness, almost competing with, with human speech. We were very limited with unit selection or hybrid unit selection in terms of flexibility, inherently due to the technology. But here with neural text-to-speech, because it's purely based on deep learning, we hope that we can push higher in terms of flexibility and expressivity. So the whole point of my talk from now on will be how to push this neural text-to-speech towards more expressivity. So this was mostly the context. I guess it's pretty, most of you know that, right? Is there any question so far, or should I move ahead? I don't see anything in the chat, so I'll assume I'll move ahead. Let me know right in Budapest if there is any question. So again, the question is how to move further in terms of expressivity and flexibility here. And so how do we modify this framework here of neural text-to-speech to make it more expressive? And I'd like to come back to this point here when I mentioned that neural vocoder is universal, or at least that's our goal, right? Universal as in the sense that we want it to be independent of the speaker or the style. So that's one of the first things we try to do. And as I said, we build upon parallel wavenet, and we want to make it universal. For that, we train the system on a multi-speaker, multilingual corpus. So something around 78 voices in 28 languages. I think we have 3 key utterances per speaker and a wide range of styles, right? On top of that, we also introduce something which we call Autoencoder. I won't go into the detail, but that's something that we use during training, and it's a VAE, so variational autoencoder type of conditioning network here that helps improving the quality. It's something we published at ICASP this year. I'm going to play, so here human recordings. You will have the speaker dependent parallel wavenet, then the parallel wavenet trained on this multi-speaker multilingual corpus, and finally the proposed universal, so means multi-speaker corpus plus also this audio encoder.
A hill can't be a valley, you know. A hill can't be a valley, you know. A hill can't be a valley, you know. A hill can't be a valley, you know.
Okay, so I guess you can make your opinion. No idea about the fidelity through the channel here, but of course we tested that, we evaluated that more thoroughly and more in a more rigorous manner. And basically first we compared here in Mushra, you have here human recordings, a speaker dependent parallel wavenet, and our proposed universal parallel wavenet. So so that means this one, right? And the goal, of course, is for the universal to be at least as good as the speaker dependent parallel wavenet. And you have here different voices like British English, female adult. And as you can see, for almost all voices, we get an improvement of universal parallel wavenet over the speaker dependent model, except for only one voice here with a very slight degradation. But on average, it's even better than the speaker dependent model, which is good because it speaks for the universality, so to say, of this neural vocoder. We also wanted to check how it goes along different styles. You have here emotional style, neutral, conversational, long form reading, news briefing, and singing. And the goal is the same, right? We want the universal to be at least as good as the speaker dependent model, which is the case for almost all styles except for long form reading. So again, I won't say it's perfectly universal, but is sufficiently good in terms of universality. And that's very great because what it means is we can almost consider the neural vocoder to be a solved problem, if I can say, in the sense that if we want to build new voices or new styles, we can purely focus on the acoustic model and consider that the neural vocoder would be good enough. So now the rest of the presentation will be around how to make the acoustic model more expressive. So if you remember, this is our architecture, grapheme to phoneme. We have the phoneme. So here we have a sequence of phonemes and punctuation marks, a main encoder, attention modeling, and autoregressive decoder. And the use case we had back in 2018 was, I presented, we have maybe more than 70 voices, right? And they are all what we call neutral voices in the sense they are not necessarily expressive or stylistic, right? But we want to create some styles for some of them. So basically we have for that voice a bunch of neutral data, and we want to also, of course, collect some stylistic data and build that stylistic TTS. And what we did was to add here a style embedding. So we have a style ID, which is a one hot vector. So let's say neutral data and stylistic data. And we have speaking style encoding, and we come up here with a style embedding, which is fed as well to the attention model on top of the, in addition to the, to the phonetic embedding here. The very first style that we released, that was end of 2018, was the newscaster style. So basically a style really dedicated to reading news. So I'm going to play the samples, the same text as before. Everything is neural text-to-speech till the end of this talk. So here we have neutral NTTS, neural text-to-speech, so neutral style, and here we have the new newscaster style.
Introducing Amazon's first custom electric delivery vehicle. Amazon has revealed its first custom electric delivery vehicle, designed and built in partnership with Rivian, and expects to have 10,000 of the new vans on the road delivering to customers as early as 2022. Introducing Amazon's first custom electric delivery vehicle. Amazon has revealed its first custom electric delivery vehicle, designed and built in partnership with Rivian, and expects to have 10,000 of the new vans on the road delivering to customers as early as 2022.
Okay, so as I guess you can hear, so intelligibility and naturalness are still very high, and we were able to capture the target style here. So then, of course, we can apply the same mechanism to develop other styles on top of newscaster. For example, we did conversational style and more. Then we wanted to go towards more emotional speech. And so that was back in 2019, if I'm not mistaken. And our first business use case was partnering with the Alexa Sport team. So the use case is the following. In Alexa, as an Alexa customer, in the settings, you can set in the preferences, which team you support, right? So let's assume I support the Hungarian team of football, right? And it's the Euro Cup. So basically, if I ask Alexa, what was the result of, Hungary, Germany yesterday? If Hungary had won, you would have an excited, upbeat, let's say, version of the rendering. If they have lost, you would have a disappointed rendering. And for each of those two emotions, we have 3 levels of intensities: low, medium, and high. The plot here is a 2D visualization of the latent space. We use a variational autoencoder, a VAE. And as you can see, the space here is both dense and continuous, which is good. So now I'm going to play for the same sentence. So we'll start from neutral, but I will go from high disappointment up to high excitement, and you will see how the whole expressivity is changed.
I am playing a single hand in what looks like a losing game. I'm playing a single hand in what looks like a losing game. I'm playing a single hand in what looks like a losing game. I'm playing a single hand in what looks like a losing game. I am playing a single hand in what looks like a losing game. I'm playing a single hand in what looks like a losing game. I'm playing a single hand in what looks like a losing game. I'm playing a single hand in what looks like a losing game.
Right, so high excitement is really if they win the Euro Cup. All right, I can go further, but I would like it to be a bit more interactive, to be honest. I mean, going to church is tomorrow. Are there any questions to me so far? I think we do have times. Okay. So I will proceed then.
Could you see the chat window? Because
I can't. Actually, I'm not receiving any notification of the chat. Sorry.
Okay. So in the chat, I saw some
okay,
questions.
now I can. Yes.
Yeah. Okay. Can you see it now?
Would you say, based on your own experience, that universal vocoder approach mentioned also works well when the input is unusual? For example, shouting, child. Okay. So the examples you provide here are something we don't have data for. So we do have a child voice. Let me check it, maybe even in the slide there. When it's out of domain, of course, it performs a bit worse. We do have singing as well, but I wouldn't be confident to say for out of domain data, as you mentioned here, it would work well because this is completely unseen during training, right? But at least as long as the data has been seen, at least for some speakers, I would say it's working well. I'm going to go back to the slide because I think I do have those answers here. Right, we do have singing, but it's not opera singing. But as you can see, we do improve definitely by a lot compared to the speaker-dependent parallel wavenet for singing. But still, if you look at the gap comparatively with human recording, it is probably lower. So that's one thing. And here I think we have adult. We do have a child voice here. Again, I don't see any problem with the speaker. I mean, we do have an improvement of the speaker dependent, but probably maybe also the ratio. No, I think it's doing okay on the child voice. So that's the only data I can have to answer that. But again, I wouldn't be confident so much about going to out of domain data. For emotional disappointed, professional actor performing data for each. Do you think there could be a more scalable and low cost approach? So indeed, we had the same voice talent. So the voice of Alexa US coming in studio and recording those two emotions with the 3 intensities. We have much less data compared to what we use with style. So the approach is not scalable in the sense we still need to to bring the voice talent in studio and to record, but using less data. So I would say it's partly scalable. Of course, as you will see in the slides, our goal is to go to more data reduction approaches and rely less on the voice talent.
There's one question about how different is this from the GST approach?
From global site token. Different is this? You mean which slide are you referring to? I guess the style, right? It's not very different actually. It's pretty much. I would say it's very comparable, right? In that sense, there is no radically different approach here. So it's comparable indeed. Okay, I think there are no more questions. Of course, if you have more questions about those slides, I would like to get back to that.
We can go on, and afterwards we can have more discussions.
Makes sense, yes. Okay, so I was at emotional TTS here. Next, we wanted to go to also celebrity voices. At the end of 2019, we released the voice of Samuel L. Jackson in the US. Recently, 1 or 2 months ago, the voice of Shaquille O'Neal and Melissa McCarthy, very famous in the US. And I think last week, right, we released Amitabh Bachchan. He is kind of a superstar in India, and it's a star of Bollywood. Why I'm adding this slide here is, contrary to our standard voices in Alexa or Polly, Amazon Polly, so AWS service, those voices are very unique in terms of personality, and they are much more expressive. So they come with additional challenges that we need to work on in terms of modeling. Whisper mode. So we are going further in terms of expressivity and more human-like interaction with the device. And the idea of the whisper mode, which we released in 2018, the idea was the following. If you whisper to Alexa as a user, you would expect Alexa to whisper back. So let's say you have similar as you would do between humans. So if you have, for whatever reason, I don't know, your baby is sleeping, you would like to whisper, so you then expect Alexa to use normal voice for that. And of course, we cannot, we cannot contact those voice talents to go back to studio and record, I don't know how many hours of whisper speech, right? That's not feasible. So our idea was, we have those normal spectrograms, spectrogram of normal voice, and we want to convert them into spectrogram of whispered voice using machine learning. The machine learning here means they are not very fancy techniques like those complex deep learning techniques we use for acoustic modeling or neural vocoding. So they were GMMs, so Gaussian mixture models, or more simple DNNs. And also the conversion. Also, we don't need a lot of data to do that. I'm talking here in less than 1 hour of data. And as you will see in the next slide, this transform here, we learn it in a universal. So by universal, I mean speaker independent way. I'm going to play samples. Those are the results we got. The first, again, the first use case was US English, almost as always. Here you have in blue, those are Mushra scores in terms of naturalness. In blue, you have human recordings of whisper. Oracle is copy synthesis of this whisper. And our baseline here in purple is DSP. So basically, at that point in time, right, if you look at the literature, there was nothing about whisper synthesis. There were a few papers, a few studies on the acoustic differences between normal speech and whisper speech. So DSP is a signal processing tool that we implemented in word vocoder to reproduce those modifications that we have seen in those studies. And here in green and red, you have the transformation based on machine learning. We build upon SP Rocket. Okay, so that's for US English. As you can see, we are even competing with Oracle, which is copy synthesis. So that's pretty good and very clear improvement over the DSP baseline, which is a weak baseline somehow. Then, as I said, we learned the technique to be speaker independent. You have the results here. SD is speaker dependent model, but you will see that the universal in orange is at least as good as the speaker dependent. We tested here on Australia, Canada, Great Britain, India, US, and more speakers. And yes, and we do confirm that the model can be speaker independent. So I'm going to play samples. It's whispers, so the volume is a bit lower. So I hope you can hear that. So this is the DSP, which I find to be a weak baseline, and based on machine learning here. So basically based on simple DNN.
Brian Sapient, above, posted video clips on YouTube showing how Uri Geller, left, uses sleight of hands to bend spoons. Brian Sapient, above, posted video clips on YouTube showing how Uri Geller, left, uses sleight of hands to bend spoons.
All right, that was for UK English. As you can hear, DSP has few artifacts because, again, it was very unexplored field, I would say. I'm going to play samples for Spanish and then Indian English.
Me podría haber ido bien con el Feng Shui, sin embargo. Even soldiers on the front line could be issued with Yomafs to protect their sensitive shell likes from noisy rifles. Even soldiers on the front line could be issued with Yomafs to protect their sensitive shell likes from noisy rifles.
Okay, I hope you can hear that properly. I'll go to this slide of singing voice synthesis, and then I will go back to possible questions. Singing voice, because of course it's still one level ahead in terms of expressivity. And actually, our approach was very similar. We built on this encoder, attention modeling, decoder, and the vocoder here at the end. The idea is we start from the score. We use a front end to build a note embedding here that goes into the encoder. The note embedding looks a bit like this. So it captures information about the phoneme, the octave, the tone itself, duration, and the progress, which is the location as part of as we progress through the word here, right, to track the location. And we got actually relatively good results. In red here, you have human recordings of singing voice. The baseline is WGAN Sing, which at that point in time was, fairly representative of the state of the art, and the proposed technique here in blue, based on this sequence-to-sequence encoder attention decoder. And as you can see, we have a significant improvement, but still a substantial gap compared to human singing. All right, like to go to questions. I can't see the chat, right? So let me check here if there is anything. Right, are there any questions at this point, or should I move ahead? I see one question. In the meantime, your whispered voices sounds like ASMR. Do you consider such application? Potentially we did, right? But not yet. ASMR is this very peculiar experience. I don't know if everyone knows about that. I can't remember what it stands for, but it's maybe the person here will be able to describe that, right? But it's basically using whisper to have, yeah, sensory, yes. But you have this, well, check on YouTube. It's a very peculiar experience. We did think about it, but so far it has not concreted. It has not been concretized into a business use case. I'll go to Gérard question. Before that, Gérard, sorry, I have one more question. Does neutral to whisper speech conversion change duration? It does not. No.
Okay. So yeah. I have a question.
I have a question. In fact, so your this whispering experiment is that it's an example of this chameleon effect where you have co-adjustment, in fact, of the voices when you are interaction. Do you have other general principle for in fact, having a co-adaptation between the speaker and the listener? So, for example, when you address to a female, your F0 is raising and so on. So, do you have some kind of general framework for working out this mutual adaptation of voices?
I do have some slide later on, Gérard, on contextual, how to leverage contextual information. So I'll present what we are doing at the moment, and I'll come back maybe to that question at that point in time. So it's coming in the next slides. I'm coming back to the previous question on changing duration. Actually, it doesn't change duration, but whisper speech is also usually slower. So we do recommend to slow down the speech rate by 5 to 10% to make it more realistic. Most kind of tests of whisper voice, we don't have most. I mean, I showed the results of Mushra. We use Mushra test for whisper. Right, I'm going to share those. The instruction, I can't remember exactly. We need to check that paper. You can find it on the archive. Was published in Signal Processing Letters. Right, so we do have those Mushra scores, right, to quantify exactly the naturalness. And again, the main conclusion is very big improvement over the purple, which is the DSP, but which I consider again as a weak baseline, and very close also to the Oracle, which is vocoded, so copy synthesis of human recordings. All right. So let's move ahead and come back to possible questions. One of the questions we had was, as a human, when you speak or when you read, you do consider, what is the grammatical structure of the sentence, and what you do understand, you do comprehend the content, right? So the question is basically how to leverage syntactic and semantic information. And the approach we had for that was very similar, basically add some embeddings here to the attention model, contextual word embeddings. So basically we rely on pre-trained language models such as BERT. We have also non-contextual like GLOVE or Word2Vec, but here you do have a semantic encoder providing an embedding to the attention model. We tried similar thing at the syntactic level, right? Basically capturing it through graphical neural networks. Everything is in this paper from ACAS 2021. So I'll come to more and more to your question, Gérard. I'm going to talk about dialogues and then how to leverage contextual information. So dialogue, we want to move away from the pure text-to-speech paradigm because as input, not only you have text, but you can leverage some additional context information. Theoretically, it can be any information about the user themselves or the environment or even more, right? So basically, not only you have text here as input, but you have some context. And one very first thing we want to do is contextual rephrasing, because Alexa is very deterministic, and going to more human-like interactions, of course, you want to adapt the response depending on the context, right? Just the text itself. And then the voice should also adapt to the context. And we have this contextual text-to-speech, which I'm going to present here. So that was the architecture here. So let's say Alexa provides an answer here, going output in the universal nerve vocoder, and it goes to the Alexa skill here, which can handle like dialogue management and more. It really depends on the Alexa skills, which can be again developed by 1P, so first party or third party developers. And the Alexa skill would generate typically a generic response from Alexa, and also can output some context features, right? So one thing we do is we rephrase the response of Alexa. So it's less generic, but we have something more adaptive here. So that means that the text here, which is input to the TTS, is a rephrase response. Additionally, we have these context features here, which are fed into the context style. We do have the context style embedding here. So very similar to what we do for the styles, right? But leveraging these contextual features. So playing a sample here, the baseline and the context-aware system.
Very happy to help. Let's find something you'll like on Amazon Music. How about something from the 80s? Does that work? Very happy to help. Let's find something you'll like on Amazon Music. How about something from the 80s? Living on a Prayer by Bon Jovi. Does that work?
So yes, the very first business use case was for Amazon Music recommendation. And those context features, again, capturing maybe the environment, the history, the user, it's something that's handled by the customer. So in that case, that was Amazon Music. But if we think about other use cases, we could theoretically leverage any context features. I don't think I'm going to play the samples here, but certainly the one of natural turn taking. And actually, I'm going to play it's a kind of mock-up. And by the way, so we released that, as I said, for Amazon Music recommendation at the end of 2020. So now I'm going to play a mock-up. So that means it shows a bit our vision in terms of natural turn taking.
Alexa, begin group conversation.
Okay, let's talk.
I want to order a specialty pizza from Mike's Pizza.
Today, Mike's Pizza has the following specialty pizzas: 3 cheese delight, pepperoni party, meat lovers.
That one.
Okay, what size?
Order a large one, please.
Sure. How about the crust? We can do thin crust, deep dish, regular, and Brooklyn style.
Regular, please.
Okay, so I have a large meat lovers with regular for $12.99. Would you like to place the order?
Yes.
Great. Completing your purchase with Amazon Pay, you'll receive an email confirmation from Mike's Pizza.
How about a movie while waiting for your pizza?
Yeah, let's see what's on. What's new on Prime Video?
How about The Lincoln Lawyer starring Matthew McConaughey?
Who directed it?
It is directed by Brad Furman.
What do you think?
Is it a good movie?
It has a rating of 7.3 on IMDb, based on 200,000 votes.
Great. Play it now.
Playing the trailer now.
So that's a mock-up really showing the direction that we are targeting. Okay, I'm going to stop screen sharing before going to the next section. Do we have questions here? You mentioned before the difference between the research team and the application team. How, where in the process do you perform the handoff? Right, so typically we as text-to-speech research team, we own generally demonstrating a capability in one voice, one local, which is generally the US English, Alexa. All right, so that means when I show you whisper, when I show you emotional or newscaster, we do start from scratch, right? We demonstrate the capability. We answer all research questions we have to, and we come up with, we own the feature release, right? We do that for one voice or maximum 2 voices. And then once this is done, we hand it over to that more production team, if I may say, that consists of language engineers and software developers, a few scientists too, and they apply that technology to more voices and more languages. Question from Javier, context aware. Right, so, okay, I'm going to read that. The context-aware voice was trained on exactly the same data or was new data recorded? We had some new data recording to capture a bit the styles that we may want for that target application.
Yeah, my question would be to that how do you find the context? So do you aim some like generic context definition, or it is just depends on the application? So actually, it's the business people who give you the context.
Right. So it's really application dependent. So we are working closely with the customers, with the technical program managers and their product manager to understand what kind of contextual features they could provide us and how we could adapt to that. Right. So it's really, in that sense, it's really business use case dependent, as any application, any Alexa skills could leverage different contexts and use them differently. I do see a question from Tomoki. Could you explain more how to rephrase responses based on context? For example, which do you use? It's not based on rules. Rule-based approach is our baseline here. So we do use techniques for based on deep learning. I don't know how much, if that has been published yet. I think Alexis could, if that, I'm not sure if that is it, I think that was submitted to EMNLP this year. I should check the status because that was sent a few days ago, but if we have anything we can share with you, Tomoki, we'll do that very soon. Question from Bastian, when the context vector comes from 3P scales, how could you train with that? Yes, that's not something we do have yet. 3P developers for contextual. So far they are only 1P, but eventually we could go with third party, but that's still something to be done. Yes, working with the customers, but eventually those customers could be third party. Does it mean that for each, question from Javier, does it mean that for each new application, new data needs to be recorded? Not necessarily, unless we want to go to styles that that are not covered. So far, we covered, I would say, different styles that could be leveraged. So as I said, like conversational styles, we have this newscaster, we do have more, and we do have those emotions. So unless the business use case requires something else, right? Something out of domain, but I would say with the existing styles we have, we can already cover a wide range of applications.
Like more business-like question that I just read news that now in many parts of the world, people used to have the first name Alexa, and now people make fun of them, especially at schools. So do you plan, or is there any idea to recover that or change the name to something which does not cause trouble for like many kids?
Right. As I said, Alexa organization is very big, so not very up to date with the progress in the wake word detection team. But also when I talk about celebrities, they each have their own wake word, right? So yeah, that's the only answer I can give for now, but maybe checking with wake word team could help. Gérard, I'll come to you, but I see a number of questions in the chat. Should I go to the chat first, maybe? Question from Javier. Have you tried to transfer the styles across voices? I'll get to that in the next slides. Alexis, censoring, I believe. Computer, I think it can be indeed, I wasn't sure, but computer can be used also as wake word. That can be set in the preferences, so in the settings. All right, can move to question from Gérard. Oh, I guess that's the reason why you stood up.
Just going back to science for a while. Two questions. Do you think that that's the answer to my question? So you have finished about this chameleon effect, or you have more slides to come?
Not on this topic. As I understood your question, right? Your question was how to leverage contextual information to how to adapt to the user. That was your example here, right?
The voice of your interlocutor.
To the voice
so
itself.
If you are speaking to a woman and you are speaking to
yes.
answering to a man, do you change the F0? Do you change the, for example, if you have an elderly person, which is you have to speak more slowly and so on. So do you adapt speech rate and so on? General mean to adapt to the voice.
Right. We do have the means, but we don't do it yet, right? Those means and this paradigm, because your question was whether we do have a framework for that, was these slides about contextual information, because eventually, you know, from DSR output, you could have those speaker characteristics that are fed then. So I should get back to slide number 3 or something like that, right? But and same for the NLU, right? You could have various information flowing down the whole architecture that are fed within text-to-speech as contextual features. But for the time being,
we have this available, but scientific question is how to exploit it. And okay, so let's move forward. A second question is about turn taking. It seems that you are perhaps too fast in answering questions. It looks like your machine doesn't has no cognitive activity. Normally, when you ask questions, nobody for the machine to be intelligent, it has to show that they are computing something, or
right.
So do you think it could be interesting to delay, in fact, your response according to the complexity of the question?
It could, yes. That was a mock-up, right? That's not something we have in prod and you know, a realistic interaction. But of course, and we can go towards also paralinguistics, having hesitations, things like that to make it more.
Yeah, the delay is interesting to think about the delay of the response. There is an impact. We have been working on human-robot interaction, and this time devoted to cognitive
right.
activity, supposedly, in fact, impacts on the degree of confidence you have in the information delivered by the robot. So I suspect that for the bot, it will be the same.
Absolutely, yes, absolutely. And this mockup, of course, we do have latency, right, in Alexa between the, so you would have that, but it's a great suggestion, right, to sort of model the cognitive load that possibly a device would have, same as a human. Thanks, Gérard, for the suggestion. All right, so I think those were only answer. I'm going to go here to, I still have a few slides. So as I said, we develop different styles, conversational, newscaster, emotions, but we have a heavy dependency upon the voice talent. We need to record a lot of data. So one of the need we have is how to make it more scalable and how to reduce the dependence upon data. And for that, we developed first techniques of prosodic transfer. So the idea is you have a source speaker and a target speaker. So let's say target is Barack Obama and the source is myself. So prosodic transfer would basically have an utterance from me, uttered by Barack Obama, but really capturing the prosodic patterns that I use and transplant them onto the voice of Barack. All right, so the technique we have for that is called copycat, published at Interspeech last year. And basically here, we have the neural text-to-speech system during training. We input the text, but also a speaker identity of the source during training and the source referent prosodic latent here. And at the output, you have speech, which is, of course, here, the voice identity of the source during training. But during inference, we feed here the identity of the target speaker. So here, Barack Obama, but using the source referent prosodic latent. So basically, the prosodic patterns that I used. And at the output, you would have the speech of the target speaker. So let me play a few samples here so you can realize what it's about. We have source prosodic reference here, the target speaker, and then the synthesize where we apply this prosodic transfer from the source to the target.
Alabama voters are heading to the polls in a special Senate election.
The state's governor says California is looking at a, quote, new normal for fire season. Alabama voters are heading to the polls in a special Senate election.
One more time.
Alabama voters are heading to the polls in a special Senate election.
The state's governor says California is looking at a, quote, new normal for fire season. Alabama voters are heading to the polls in a special Senate election.
The other way around.
The state's governor says California is looking at a, quote, new normal for fire season.
Alabama voters are heading to the polls in a special Senate election. The state's governor says California is looking at a, quote, new normal for fire season.
Right. So, I mean, I assume you got that, right? We really transfer the prosody and maintain sufficiently good speaker similarity here. So we use 3 dimensions here to evaluate that. This technique of prosody transfer through Mashra scores. Here you have naturalness. We check also how efficient was the prosody transfer itself. And finally, we want to make sure there is no speaker leakage, so we measure the speaker similarity. And that's very good to have such a technique of prosody transfer because we use that for data reduction. So here the use case is, you know, Barack. Let's focus on Barack. Barack Obama. We can't bring him in studio for so long. He's busy as we all are, but probably a bit more. So we can have, let's say, 1 hour only of, or even half an hour of Barack's voice. But we do have on the side, we have, I don't know, 10 hours of my voice and 10 hours of John's voice, right? So the idea is we would use those techniques of prosody transfer to convert the recordings from my voice into Barack Obama's and the recordings of John's voice into Barack Obama's, right? So that means that for training, not only you have half an hour of real speech from Barack Obama, but you have also 10 plus 10, so 20 hours of artificially converted data using this prosody transfer technique. So basically it's data augmentation using voice conversion, and we use this synthetic data on top of the available recordings for that voice, right? And as a last step, we perform fine tuning only on the target recordings for that voice. So we are going to compare 3 systems here, human recordings, non-data reduced. So that means training neural text-to-speech as usual on the full set of data that we would have. And our methodology here, where we have data reduction, we use only half an hour, but we apply this voice conversion plus fine tuning. Results here, I'm going to, don't worry, there are many numbers, but basically we measure naturalness and speaker similarity. I'm going to focus here on the very bottom on the large scenario. So basically we have 5 hours to train the non-data reduced, and we can reduce data to half an hour for the data reduction. So let's see here naturalness. So as you can see, human recordings is very high, is the upper anchor. We get something like 81 point. Non-data reduced, so neural text-to-speech trained on 5 hours, we get something around 55. And last row, we have data reduction. So we have only half an hour of the target speaker, but we use this voice conversion and fine tuning. And good news is it's significant. We have, 59 plus. So it outperforms significantly the non-data reduced scenario, even though we have much less. We have 10 times less data compared to the non-data reduced scenario. Some sample to illustrate that, and on newscaster, here we have the baseline trained only on half an hour of target recordings. So that means it's pure neural text-to-speech, and then applying data reduction for newscaster side.
Hello, here is your evening breaking news. The man suspected of fatally shooting a Denver police officer is still on the run. The FBI team is actively looking for him in Colorado Springs after someone called to report seeing a man breaking into a vehicle in the area. The suspect is facing a lifelong sentence. This was Emma Taylor. Please keep following us for more updates. Hello, here is your evening breaking news. the man suspected of fatally shooting a Denver police officer is still on the run. An FBI team is actively looking for him in Colorado Springs after someone called to report seeing a man breaking into a vehicle in the area. The suspect is facing a lifelong sentence. This was Emma Taylor. Please keep following us for more updates.
So as you could hear, there were significant glitches. So the artifact harshness here in the baseline, they are reduced definitely by data reduction. Conversational here, the baselines are built on 5 hours or 1 hour and a half for the target recordings. And for data reduction, we have only half an hour for the target.
It's good that she's played her before and that she's beaten her. It's good that she's played her before and that she's beaten her.
Olympic Games, welcome home. Olympic Games, welcome home.
So again, I hope you could reflect why naturalness was increased in the results. I'm done. Last message, we are hiring. So if you're interested, just email me. Best email address in the world, drugman@amazon.com. Thank you. Thanks a lot for your attention. And I think we can move to the questions.
Thank you, Thomas, for the presentation. I also ask and hope that we can share your slides with the audience, so that if you would just send it to us. In the meantime, I ask first the people who are here, if you have any questions left. So not here, maybe? Yeah, and ask those who come here just to introduce yourself, because the others maybe don't know you.
Yeah, my name is Grant Reber. This is actually a question I asked before to another speaker, but I just want to ask you. I was curious with the parallel wavenet, when you use the conditioning on the VAE, is that something you see as important really because it's in this distillation framework, or is that useful just for like a conventional wavenet too?
Right, good question. The author is just there, it's Slava. I guess just the more depth, right? I had only distance supervision of that work, so I don't know exactly, but I assume this audio. So basically the question, Slava, is whether this audio encoder that you use for the universal power wavenet, whether we could, use it for other nerve encoders, right? That's basically your question. I guess the question is yes, right? Slava, do you disagree with that?
So I think it's more useful for distillation indeed. We found that. I think for the other types of vocoders, we might need to revisit to learn more whether it requires this factorization or not.
Thanks, Slava.
Congratulations that at least one person from Amazon team came here on site, and I encourage those who have not decided yet whether they come to Brno, that they can still consider, because I think Central Europe is quite safe, so you can try. Online questions?
I can't see any, and I wish I would be with you guys today. I have really personal reasons. My third baby is coming very soon, so I need to stay here. But yes, it would be so awesome to be on site. I don't see any question from the chat. If there is no one on site, then I think we are good.
Yeah, Gérard has one more.
Just because I like you,
Of course.
So of course. Did you follow this discussion about phonemes as input? So I was arguing that phonetic choice is a part of a style, in fact. So it's somehow a symptom of your mastery of the language. So right. The choice of phonological variants is in fact also adapts to the person you are speaking to and so on. So I was questioning about the choice of having a separate generation grapheme to phoneme transcript and the style information, which is okay, in the next future will be adaptative, speaker adaptative. So you will, what is your policy? So you have a vision of for 3 or 4 years. So did you think about this? Is that part of your?
So basically, what you're saying is the grapheme to phoneme and the style should not be considered as separate, but rather share. I can't hear you.
It's part of the style. It's part of, depending of your address to a guy, somebody who is mastering the language, a customer, you know, which is just a native speaker of in the US, or an immigrant, a fresh immigrant. So you don't perhaps choose the same variant of a pronunciation because you have to adapt, in fact, to the person. So and so prosody, phonological variation, and so on is really part of the same policy of adaptation to your listener.
Right. I guess it's more a business question to product manager. Of course, we want to adapt to variants like dialects and so on, but do we really want to have the agent like Alexa for non-native to adapt to? I don't know, right? It's how you position the product. I'm even questioning whether we want to. For some use cases, we could, right? Like dialects. I don't know if you go to Harish and so forth. But do we really want to do that for non-native? I don't know. You have plenty in the US, right? I doubt so personally.
Oh, you? Okay.
But,
so clients of pizzeria are variant, you know.
It's actually a question to business, right? Because at the end is how I don't know, the relationship between the agent and the customers, right? If I would be a Belgian immigrant in the US, I'm not sure I would expect Alexa to adapt. It's questionable, right? Not saying I have the answer here, but I would say it's more a question to a product manager to business.
Product manager, okay.
You disagree with that?
You know, interactive speech is the future of speech technology. Sincerely. I will be retired, but I think in 10 years' time, all the technology we have been so far performing will be okay. So anyway,
no, I agree with you.
Talk to your manager.
Yeah, he will be retired too in 10 years. But
question to you.
Yeah. Just saying, I do agree with that. I was just disagreeing whether an agent should just adapt to non-native speakers or how, to what extent, right? I'm just saying there is a business question behind that. Yes.
Yeah, I would repeat just I asked a previous question, but I'm not sure you were there. It would be the variability of the speaker. So I think that people get bored from text-to-speech basically because it is deterministic. So if you give one input, you always get exactly the same output. And the variation is currently done just on a random basis. And it is either not noticeable, or if it is noticeable, then it will make it worse. So then do you have any strategy or do you have any vision of providing more variability so that there could be longer term interactions?
We do have that, right? As I had 2 slides on adaptive and contextual information. As I said, the very first release was the very end of last year, 2020. So it's less than 1 year, but it's definitely a direction that we are exploring, how to adapt to the customer and how to be less deterministic, have more, you know, this rephrasing, this adaptive response, definitely going to the direction. I'm just saying it's the beginning, and there are multiple business, not only science questions to answer, but business and UX, right? Because or CX, customer experience. I'm just saying I don't have those answers. We will need to check with those teams, but that's definitely a direction we are moving to. Is just, you know, the early days.
Yeah, thank you. So that can be like a topic we can work on. And there was one more question. Know that models that use a VAE reference encoder can sample variation of prosody for the same input. Yeah, okay. We'll see whether it works. Any more questions? Yeah, one more.
Hi, yeah, I was just wondering if you've explored these kind of voice conversion type techniques for generating more emotional data.
More emotional. Do we have that? We are considering that. So far we do, right? Presentation from Bastian Schnell as part of this workshop. We did that. We went to the direction. I mean, the samples I've shown here were only for stylistics. You have heard conversational, you have heard newscaster, but you could apply that also for emotional. Bastian Schnell, I think, was intern in my team last year and was working also in that direction. Am I right? He presented the paper on that like yesterday or on Thursday, right? I guess people can confirm. Yes, EmoCat, language agnostic emotional voice conversion. So I think he presented that on the first day on Thursday. So you could check that. EmoCat. And you have the archive link here.
Actually, I saw that talk. Somehow I was, yeah.
Right.
Thank you very much. So last opportunity to ask questions. No more questions. So thank you, Thomas, and wish you a nice weekend. And thank you for sacrificing your weekend for this talk, which was really very interesting. And look forward to continue at in 1 hour. So actually we used about 10 minutes, I think, from the break. So those who are online and who don't need that much time for lunch, they can go to spatial chat and there continue to have a discussion. And then this program will be continued at 1 p.m. plus 10 minutes. Okay, thank you very much.
Thanks to everyone. Thank you, guys.